Okay, yes. So, good morning once again after the coffee break from Corfu. I'm Andrzej Sitas and I'm the chairman of this last morning session. And we are very happy to start with a talk by Kevin Morand from Seoul on a graph complexes and deformation quantization of the bialgebroids. You have 20 minutes, so I'll give you warning after, say, 12 minutes. Okay? Thank you.
Okay, perfect. Okay, thank you very much.
It's yours, and you're live on YouTube.
Okay, thank you very much. Yeah, so first of all, I would like to deeply thank the organizers for this very nice workshop. So it's a pleasure for me to be a part of it and to be able to present these results that have been obtained within the context of deformation quantization, and more precisely regarding the quantization of the bialgebroids and how graph complexes can provide some information there. Okay, so before going to the detail of this result, I would like to start with some quite generic statements regarding deformation quantization of Poisson manifold, and more precisely the Concevic formative theorem, which, as maybe some of you know, so provides some explicit Lie-infinity quasi-isomorphism denoted U between two differential Lie algebra, T poly on the one hand and D poly on the other hand. So this is the so-called formality map provided by Concevic, which relates these two objects, T poly, which stands for the Schouten-Grady algebra of polyvector field, which controls the deformation of Poisson bivectors, and D poly, which stands for the Orshi differential Lie algebra of multi-differential operators, and which controls star products, basically. So we have this relation between these two, and correspondingly, we have some relation between Poisson structures and star products. So more precisely, a corollary of this formative theorem is that it provides a canonical bijective map between formal Poisson structures on the one hand and star products on the other hand. Okay, so let me recall that formal Poisson structures are formal series of bivectors, formal series in the formal parameters H bar, such that this formal power series is nilpotent with respect to the Schouten bracket. So in particular, this enforces the fact that P1 should be a Poisson bivector. Okay, so in particular, if we have a Poisson bivector, then we can construct the formal Poisson structure, the most simple, which is just H bar pi, which is formal Poisson structure. It goes under the Schouten bracket, and then we can plug it into this formula and obtain a star product. And this star product will provide the canonical quantization for our Poisson bivector. So this is precisely the Concevic canonical quantization formula, which is given by a star product, so formal H bar of multi-differential operators and bidifferential operators acting on two functions f and g. Okay, so let me just flash the main formula for the lowest order. So this is the Concevic star product formula that we obtain. And so we have this quantum object, the star product, which quantizes the Poisson bracket. So it is a formal power series, as I mentioned. And at the zeroth order, we recover the classical product, so the product of function of the manifold, which is commutative and associative. But the star product is a deformation zeroth, and it is non-commutative. So it is still associative, but we relax the commutativity condition. Okay, and so at first order in H bar, we recover the Poisson bivector acting on two functions. So this is nothing but the Poisson bracket associated to pi, which acts on two functions f and g. So here I chose a kind of graphical depiction where each edge, each arrow stands for a partial derivative. So pi is a bivector, so it can yield two partial differential, which acts on f and g in this case. Okay, so this is the first order, and we have many higher orders, which are all given by this type of graph expansion, where the vertices are decorated by this Poisson bivector. Okay, so overall, the quantization formula that we obtain provides some associative product on the space of function. So star is associative. It is also a universal formula in the sense that it is valid for any Poisson bivector pi and in any finite dimension. So we can decorate the vertices by any Poisson bivector, and still this will yield a quantization. Also, the coefficients that appear here are universal, so they do not depend on the dimension, as long as the dimension is finite. As we see, there is some obstruction to quantize in infinite dimension, which is due principally to this kind of cycle graphs, which generate some traces which are ill-defined in infinite dimension. Okay, and finally, this formula is a transcendental. So these particular weights, so these coefficients, are computed using some integrals over some configuration spaces of points. or more generally, they are computed using so-called Drinfeld associators, which are somehow mysterious algebraic objects that show up in different problems of quantization. Okay, let me just mention that this formula can be interpreted as a Feynman diagram expansion, which is associated to the BV quantization of the so-called Poisson sigma model formulated by Ikeda and Schreier-Strobel, which is a Poisson sigma model where the source has dimension d equal 2. So this d equal 2 will be important in the following. We will see some other example where d equals 3, for example, for Lie bialgebroids or Lie bialgebroids, in which the corresponding AKZ sigma model has a source of dimension d equals 3. So this has been explicitly shown by Gaetano and Fiore in 1999. Okay, some further comments about this formality theorem is the fact that it provides some existence results regarding existence of formality map. So this is a formality theorem. In fact, there exists such a formality map. So this settles positively the formality conjecture that Kontsevich formulated in 1993, and it provides a complete solution to the deformation quantization problem for Poisson manifolds, which was formulated 20 years before. Okay, so this is about existence. So now what about classification? So one may ask, is the Kontsevich formality map unique, or is there some space of quantization? Or in other words, is the canonical Kontsevich quantization map really canonical? In fact, it is not, and as shown by Kontsevich when formulated the formality conjecture, it shows that in fact one can act on the space of formal Poisson structure. So on this T-poly side, we can act using some particular cocycles in a suitable graph complex that I denoted GC2. Here the 2 stand for the D equal 2 of the corresponding source of the dimension of the source of the corresponding AKZ sigma model. Okay, so let me just provide an example of this. So the simplest graph cocycle in this relevant graph complex is given by the tetrahedron graph, which takes this form. And using this graph, we can act on any formal Poisson structure in order to yield a new formal Poisson structure. In particular, if we have a Poisson bivector, we can act on the canonical formal Poisson structure, the one we used to obtain a quantization earlier. So h bar pi, this is a formal Poisson structure. We can act on it by exponentiating this graph. And what we obtain is a new formal Poisson structure, which is a deformation of the original one. So we have h bar pi as order 1, but we have some higher order terms, which are non-trivial. And one can check that since we have a cocycle here, that this graph is a cocycle, and also using the fact that pi satisfies the Jacobian entity, so pi is a Poisson vector, then one can check that indeed pi h bar is a formal Poisson structure. So it is nilpotent with respect to the Schraton bracket. Okay, and this formula, I mean, how do we find these higher order terms? Just by applying the graph as follows. So this particular, I mean, this first order deformation term in order 4 can be obtained simply by acting on Poisson bivectors using this graph. So we orient our graph in all possible ways, and each arrow becomes a partial differential, and we decorate the vertices by Poisson bivectors. And this yields a new bivector, which is not Poisson, but which is a Lichner-Ovitz cocycle. So it satisfies this equation. Again, as a consequence of the fact that pi satisfies the Jacobian entity. So in a sense, this provides a way to universally deform formal Poisson structures. So we can act on T-poly by this using these graphs. But then we can also apply the quantization formula. So if we apply the quantization formula of Kontsevich to this new formal Poisson structure, then we obtain a new star product. And a priori, generically, the star product, star prime, obtained from the quantization of this deformed formal Poisson structure is inequivalent to the canonical star product. So this provides a way to act on the space of canonical quantization. So this group, the exponential group of this cohomology, acts on the space of canonical quantization. And more generally, it acts on the space of these formality maps. Okay, so one can wonder, can we compute this cohomology? And in fact, this has been done by Vivaher. This is a very important result, that the zeroth order cohomology of this graph complex is isomorphic to the so-called Grothendieck Teichmüller algebra that has been introduced by Drinfeld, and which again shows up in many areas of mathematics, but in particular in deformation quantization. Okay, so let me just briefly sum up the main idea of this talk. So basically, I want to convince you that if we're interested in deformation quantization problems, more specifically in universal solutions to deformation quantization problems. So by universal, I mean solutions which are given in terms of graphs, so expansion in terms of graphs, which are valid for any dimension and any structures, like the Kontsevich one. So if we're interested in this kind of deformation quantization problems, then these are characterized by the cohomology of suitable graph complexes that we denote GC for graph complex generically. So more precisely, what I mean by that is that we can study the obstructions to the existence of quantization, universal quantization, by studying the first order cohomology. So the obstructions to quantization will live in this first order cohomology. And if there exists some such universal solutions, these are classified by the zero further cohomology. So again, we can map some deformation quantization problem to the study of the cohomology of suitable graph complexes. So this approach is not new. It has been successfully applied in the past to several deformation quantization problems. So for Poisson manifolds originally as pioneered by Kontsevich in 1993, but also for Poisson manifolds in infinite dimensions. And in this case, it can be shown that indeed there is some obstruction. So H1 is not zero. So there is a non-trivial obstruction, which is heat, which means that we cannot quantize Poisson manifolds in infinite dimension using universal solutions. This has also been used successfully to Lie bialgebroids. And in this story, I would like to add two threads to this ongoing story by focusing on Lie bialgebroids, which are a common generalization of Lie bialgebroids and Poisson manifolds, and also some further generalization of Lie bialgebroids known as quasi-Lie bialgebroids. And more precisely, I mean, we can sum up the results like this. So again, deformation quantization problems can be somehow partitioned into different categories according to the cohomology of the graph complex that acts on them. And basically, there are two categories that we can consider. One is a so-called yes-go category, in which everything works fine. And there is a no-go category, in which there is some obstruction to quantization. So in this yes-go category, conjecturally, there is no obstruction. So H1 is conjecturally zero. And also, it is not trivial quantization in the fact that there is this infinite-dimensional Grothendieck-Müller group that acts on the space of quantization. So belong to this yes-go class, the Poisson manifolds in finite dimensions, but also Lie bialgebras and their generalization quasi-Lie bialgebra. So for any of these examples, we know some particular, we know some quantization, and we know a generic procedure to associate to a Drinfeld associator some quantization map on which act this Grothendieck-Müller group. Okay, and the second category is a so-called no-go category because H1 is not zero and there is some obstruction. And if this obstruction is hit, that means there is no quantization. This is the case for Poisson manifolds in infinite dimension. Okay, so all of these cases have already been discussed in the literature. What I would like to add is these two further cases. The one of Lie bialgebroids, which, as I mentioned, generalize Poisson and Lie bialgebras. So one could expect that indeed this belongs to the same category. But in fact, I would like to show that somehow unexpectedly, it belongs to this no-go class. That means there exists some obstruction to the quantization of Lie bialgebroids. But so this is somehow a no-go result. But if we move to quasi-Lie bialgebroids, then we have a yes-go result in the sense that quasi-Lie bialgebroids, generically the obstruction, conjecturally the obstruction is not, there is no obstruction to quantization. So these belong to the right class, yes-go class. Okay, let me just briefly review the notion of Lie bialgebroids before going further. So as I mentioned, this is a natural candidate to unify Poisson manifolds on the one hand and Lie bialgebras on the other hand. Okay, so recall that a Lie algebroid is a vector bundle, so E on the base manifold M, which is endowed with two structures. An anchor, which is a morphism of vector bundles between E and the tangent bundle of M, and some brackets, which acts on the space of sections on the vector bundle. And these brackets satisfy this further property, so it is in fact a Lie bracket. So the space of section is a Lie algebra. It is Q-symmetric and satisfies the Jacobi identity. And also, it satisfies the Leibniz rule, where we use the anchor in order to write the Leibniz term. Okay, so particular examples of Lie algebroids are, of course, Lie algebras. When M is just a point, then E is just a vector space, and we recover the usual notion of Lie algebra. Also, the tangent bundle of M is also a Lie algebroid with where the anchor is just the identity from Tm to itself. And less trivially, the cotangent bundle of a Poisson manifold is also a Lie algebroid. Okay, now the notion of Lie bialgebroid combines somehow two notions of Lie algebroid. So we have a vector bundle such that there is a Lie algebroid structure on E and another Lie algebroid structures on E star on the dual. And these two are compatible in a certain way. They should satisfy some quadratic compatibility condition. So again, example of these are Lie bialgebras. When M is just a point, we recover the usual notion of Lie bialgebra. And also, these two examples of Tm and T star M, in fact, satisfy this quadratic compatibility condition. So that means that for any Poisson manifold, we can associate a Lie bialgebroid. Okay, so these Lie bialgebraic structure are natural in the sense that they admit they can be recast using the graded geometry language as Hamiltonian function on some particular graded symplectic manifold. So the graded symplectic manifold we have to consider is this one, T star 2 E1, where E is a vector bundle. This is graded symplectic with this symplectic form. So there are two sets of coordinates and momenta, x and p, and psi and zeta. We can consider the graded Poisson bracket associated to this symplectic form. This is a so-called big bracket, which was known in the literature before this graded symplectic interpretation. And also we can define some Hamiltonian function on this manifold. So this is a function of degree 3. And so we can write this Hamiltonian function and interpret each of these terms as structure constants for the Lie algebraic structure on E for rho and F. This provides structure constant for the anchor and the bracket on E. And dually, R and C provide the structure constants for the Lie algebraic structure on E star. And if we impose that H is a Hamiltonian function, that means it is nilpotent with respect to the big bracket, then we recover the compatibility condition. So Hamiltonian function on one-to-one correspondence of this type are in one-to-one correspondence with Lie bialgebroids. So examples are, of course, Lie bialgebra, where there's no x dependence and there is no anchor terms. And also for Poisson manifolds, then pi plays the role of anchor on the dual, and we have this expression. And this can be shown to be Hamiltonian using the Jacobian entity. Okay, but what? Sorry.
Close to the end of your time.
Okay, then let me go a bit further. Okay, so okay, I will be quick. So there is a further notion of quasi-Lie bialgebraic. If we had some terms which are order 3 in psi and zeta. So this generalizes the notion of quasi-Lie bialgebraic. In particular, twisted Poisson manifolds belong to this class of quasi-Lie bialgebraic. Okay, so there is a quantization problem for Lie bialgebraics, which generalizes the quantization problem for Lie bialgebra and Poisson manifolds. So this has been formulated by Ping-Su in 1997, but it is still open in full generality. So there is no known solution to these quantization problems yet. But we can formulate two conjectures. The fact that, first of all, every Lie bialgebroid is quantizable. So this has been formulated by Xu in 1997, that we can always quantize Lie bialgebroids. And also, due to the fact that this generalizes quantization problem for Lie bialgebra and Poisson manifolds, we can expect that the space of quantization is acted upon by this GRT1 group. But in fact, I mean, the main result of this talk is I would like to argue that these two conjectures are probably false. Okay, we now have the time to give details of the proof, but let me jump to the conclusion. Basically, the idea is that to act on Lie bialgebraids, we have to resort on this kind of graphs, which has two oriented colors. And in order to act on Lie bialgebraids, we need to orient both directions. We need to eliminate all cycles, and this changes the cohomology. And in fact, this can be shown to yield an obstruction to the quantization of Lie bialgebraids. So whereas for quasi-Lie bialgebraids, then this is a different cohomology acting on it. And in fact, we can show that the Grothendieck mirror group acts on the deformation complex and that there is no obstruction. Okay, let me sum up the conclusion. So, okay, I would like to argue that this deformation quantization problem can be, again, partitioned into these two categories. And I would like to use this idea of graph complexes in order to show that there is a potential obstruction to the existence of universal quantizations for Lie bialgebraids, which is slightly surprising because, again, for Poisson and Lie bialgebra, there is no obstruction. And also, the Grothendieck mirror group plays no role in the classification of. So even if the obstruction is not hit, so if there exists quantization, then there is no action of GRT1, which is a bit surprising. So this allows to formulate the conjecture that there are no universal quantization of Lie bialgebraids as quantum groupoids. So this is a bit no-go result, but a more yes-go result is the fact that if we extend the notion to quasi-Lie bialgebraids, then the quantization problem is similar to the one of Lie bialgebra. So conjecturally, there is no obstruction to the existence of universal quantization. And also the Grothendieck mirror group acts on the space of quasi-Lie bialgebra. So we can formulate the following conjecture that given the infinite scatter, we can always quantize quasi-Lie bialgebraids. Okay, I'm sorry if I went over time, and I thank you for your attention.
Okay, thank you very much. And we have time for one short question, possibly. One short question from the audience. Sir? There appear to be no questions from here. Let me check whether there are some questions online. There are no questions online. Let me ask very, very short, very naive questions. I mean, if you have this first homology group 0, and then you use the zeroth group to classify the different quantizations, I mean, would you say that they give the equivalent products? It means that the algebras are isomorphic to each other, or?
Sorry, no. So you mean for the Poisson case?
Yeah, I mean for the general case. I mean for the general case of quantization, right? For the Poisson case, for instance, yeah.
Right. So okay. So it acts on the space of quantization. That means that a priori you obtain, if you use the canonical quantization, you obtain a different inequivalent star product.
Oh, inequivalent. They are not
inequivalent. No, they are not isomorphic.
Okay.
No, they do not belong to, only for special types of Poisson manifold, such as I mean constant Poisson manifold. Of course, they are quantized by the Moya star product, so we obtain the same quantization. Also for the linear case, we obtain the good star product. But for a generic Poisson bivector, then we obtain an inequivalent star product. So there is really some non-trivial action on the space of quantization by this Grothendieck mirror group.
All right. I mean, in this case, probably nothing is known about the completion if you have some topological product that like a sister algebra, or I mean, this is quite rare in this case.
Right. So this is very. I mean, this is formal. I mean, formal deformation quantization. Yeah, so this is very preliminary to the star. Yeah,
okay. Okay. Thank you very much.
Okay. Thank you
very much once again. And we move to our local speaker. And we can get one. We need to start sharing the screen, and you can. No, that's not. That's not it. We are ready. Okay, so why? Yeah. So we are ready to start the second talk of this session in a beautiful Corfu with a local speaker, Gaetano Fiore. We are happy to have you here, Gaetano, in person. And through the transmission, you can see that he's really here. Twisted submanifolds so far. And please, the floor and the screen are yours, Gaetano. And I give you the question as well.
Thank you, Andre. Thank you. Thanks to all organizers. Let me first address and pay homage to John Mador, who was really a very dear friend of us, of all of us, and with whom I first started to work a little bit on Riemannian non-commutative geometry. So the notion of submanifolds is in commutative geometry is certainly paramount for physics. Just think of, for instance, equipotential hypersurfaces, wavefronts for wave equations, initial and boundary conditions for PDEs, the formulation of Huygens or holographic principles, and so on. And in commutative geometry, a metric on M uniquely induces one on a submanifold N. In particular, if M is Lorentzian, we have important submanifolds like null hypersurfaces and so on. On the other hand, everybody in the audience, I think, is convinced that non-commutative geometry is a suitable framework as for developing a theory of quantum space-time, allowing quantum gravity formulation and unifications of fundamental interaction, etc. So a natural question is when a notion of submanifold is possible and fruitful in non-commutative geometry. So far, there are many examples, but I would say there has been little attention to a general answer, with a few exceptions, in particular a paper by Masson in '95. For instance, we know that the quantum group SUQN can be obtained from, so special unitary transformation, quantized, can be obtained from the one of unitary transformations by modeling out the relation that Q determinant B1. And so it would be natural to expect that any covariant differential calculus on such an algebra has the same dimension as the commutative counterpart. But this is not the case for a quantum group bicovariant differential calculus, which keeps the dimension in n square. A similar phenomenon appears, for instance, when you want to obtain a quantum Euclidean space from a sphere from the quantum Euclidean space by modeling out the relations that the square distance from the origin is 1. You cannot impose that the differential of r square is 0. Even if you take it, this differential, which is non-zero, this is the so-called Dirac operator, in the sense that you can realize the exterior derivative as the commutator, graded commutator with such an element. That's why trying to give a general answer to this problem is important. Here we give a general answer only in the framework of Drinfeld twisting of the group of diffeomorphisms, so Hopf algebra of diffeomorphisms on the manifold M and its comodule algebras using a triangular twist. And this answer, so we are using in this sense the machinery and the procedure of works of Basquieri and Vess et al. Of 2006. And the answer is also an answer in the framework of deformation quantization. We stick to embedded submanifolds over N because by Whitney theorems, osmosis M can be embedded in Rn with sufficiently high dimension N. We assume that M consists of points fulfilling a set of smooth equations Fa of x equals 0. We assume that the Jacobian of from F of F from Rn to Rk is of maximal rank on all of Rn, or if not so, we restrict the submanifolds to one on a subset, the F open subset where J is of rank K. So in our examples, the complement of the F is will be of empty, well, zero measure in particular empty. Actually, one can obtain a whole k-parameter family of embedded manifolds MC, which are level sets of F, by replacing in the equation 1 f by f minus c, some constant. And you can find embedded submanifolds n in M, simply adding more equations to 1. So our approach will consist in giving a twist deformation of Rn and of M and possibly of N defined globally within Rn. But in principle, one could do this also patchwise. The first preliminary result we have proved is that the ideal of smooth functions vanishing on this submanifold M is spanned by the functions fa themselves. Okay, we can express the algebra of functions on M as a quotient, the quotient 3. And similarly for the ones on submanifold N of M. And then we can identifying vector fields on manifolds as first order differential operators. We can introduce the Lie algebra of smooth vector fields psi on the whole Rn or in its open subset df. The tangent, I mean the Lie subalgebra consisting of vector fields which map C into C. The Lie ideal and type bimodule of vector fields which map any vector field into C, and then define as usual vector fields on the submanifold as a quotient between psi C and psi CC. So the Mathon in his work adopts these definitions, 3 and 4, to define non-commutative submanifolds as well. And we will do the same here. Okay, one can replace the smooth setting with a polynomial setting by assuming Fa is a suitable reducible polynomial in X and chi to be the polynomial functions on Rn. Then everything goes through essentially in the same way. There is an analogous decomposition theorem. Yes, I forgot to say that these results are joint work with Thomas Weber and partially with Davide Franco in Naples. Okay, so now what is the essential requirement of a deformation quantization applied to, for instance, to the algebra functions on a manifold? Is that the deformed algebra coincides with the undeformed one as a vector space, or better, as a Cn module, a module on a ring of power series in the deformation parameter nu. Whereas the pointwise product, which is commutative in class theory, is deformed into a possibly general non-commutative but still associative one, defined in this way as in 6, using bidifferential operators. We wish to that our deformed algebra functions on M is on one side still can still be obtained as a quotient, and that it still coincides as a vector space, as a Cn module with the undeformed one. For this, it suffices that the deformed ideal coincides with the undeformed one as a Cn module. And this is fulfilled if the star product between a generic function and the Fa coincides with the undeformed one. Note, let me stress that requiring that such a product belong to the C of nu, instead of A, it is not enough. So this is a stronger requirement. So if it is fulfilled, as a bonus, we obtain that taking a quotient and deforming the product are commute as operations. So we try to do deformation quantization via Drinfeld twisting. So in general, this means to adopt, to define the star product using as the bidifferential operators coming from a two-cycle twist. We on some based on some universal enveloping algebra UG. In the work of Aschieri et al., G is the algebra tangent of vector fields on M. So diffeomorphism of the algebra of the group of diffeomorphisms on M. Now, psi M in our definition is a quotient of psi C and psi CC. Can we use any element in psi C to define the twist? The answer is not. What we have found is that we must use a Lie subalgebra psi T of psi C, which is defined as a set of elements of psi which annihilate F, all the F's, and then automatically also the FC's, the translated, the shifted one. And this means this is the algebra of vector fields in Rn which are tangent to all submanifolds in the family MC. And then adopt the previous formulas to define both the algebra functions and the vector fields. And as a bonus, again, taking a quotient and deforming commute. So after this longer introduction, let me go on and add some preliminaries, and then I present the main results with also some examples. Well, some other ingredients, preliminaries would regard off algebras, which I assume everybody knows, and also the differential, twisted differential geometry as in Aschieri and West. And let me just very briefly flash on their results. They deform the algebra of the diffeomorphism, the off algebra diffeomorphism, into a non-commutative and non-commutative one, a triangular one, which is actually two isomorphic ones one can use. They apply the star product to deform all the modules of such a Hopf algebras, and also deform the tensor products into star tensor products. This applies also to deform tensor fields into star tensor fields made out of forms and vector fields. So these are multi forms of generic rank, degree, and multi-vector field. Whereas the differential, the exterior derivative remains undeformed. You deform the Lie derivative into a star Lie derivative. You have a notion of a star Lie algebra. You have a notion of star pairing between forms and vector fields, which can be extended to higher powers. And you have a notion of a twisted connection acting on any tensor field, which fulfills a number of properties, which are listed here, and which reduce the ordinary one when the deformation parameter goes to 0. You have a twisted notion of torsion, curvature, and associated Ricci and a tensor and Ricci scalar. This torsion and curvature can be seen both as maps from vector fields, for instance, times vector fields into vector fields, or as elements in the wedge product of forms. and you have the notion of a metric, and which mimics the classical one. You can obtain a rich tensor from curvature tensor by contraction with the dual pairing and so on. Okay, so let's come to our applications of these notions to differential geometries on submanifolds of Rn. So we use, as said, such a twist with the psi t, which are tangent fields to all the MCs, all the submanifolds in the family. And we define this way vector fields, as I already said. And these are Lie subalgebras. Both CT star and CM star are Lie subalgebras of psi star. You can define, so to say, perpendicular one forms by requiring that they are have vanishing pairing with tangent vector fields as usual, and this bimodule, subbimodule splits. I mean, can be decomposed in this way. All these objects coincide with their undeformed counterparts are Cn modules, and all these Lie algebras and bimodules and their associated exterior algebras are equivalent under the deformed diffeomorphisms. Now, considering a metric, possibility, of a metric, okay, a metric G on Rn gives a metric on the submanifold, the first fundamental form, right, just by restriction. It might be, we have to avoid points where this might be degenerate, so we avoid these points and consider only submanifolds where GT is non-degenerate. Starting from from the Levi-Civita connection on Rn, we can project it on the submanifold. We also introduce a Lie subalgebra of psi t made out of killing vectors of the metric. So these are isometries of the metric essentially. And okay, so 5 minutes. Okay, we can introduce perpendicular vector fields and tangent one forms in the standard way. We may ask if this construction, the decomposition into perpendicular and tangent, is covariant under the whole quantum group of diffeomorphisms or not. The answer is no. In general, we have to restrict. This is the case only if we restrict F to be based on the killing vector fields. So this is one result. Then everything goes through, and projecting on tangent or orthogonal components commutes with twisting. So also, all these objects coincide with their undeformed counterparts are Cn modules. We can then introduce also a second fundamental form in the standard way, project the connection on the submanifold in the standard way, and all these objects are equivalent under the restricted quantum group of isometries, and we, as usual, we can interpret the second fundamental form to give the twisted extrinsic curvature, and the first fundamental for the twisted intrinsic curvature. And we can prove a twisted Gauss equation, which allows to compute the twisted curvature on the submanifolds. It has the one on the Rn and of the second fundamental form. Everything can be made more explicit by by constructing explicit basis or a complete set of forms or vector fields in the tangent and the normal part. In particular, one set, complete set, I mean, not always it's possible to construct a globally defined basis. Of course, this is not possible if M is not parallelizable, so you have to work with just with complete sets. And one convenient complete set, which is independent from the introduction of a metric, is consists of objects which mimic the angular momentum components. So they are defined in the case of codimension 1, they are defined as this combination where Fi is the derivative of with respect to xi of f. Yeah, and so on. Then okay, we have to apply what I have studied 20 minutes ago. I studied quite late anyway. Okay. So we can do everything very concrete and apply in particular these concepts to twisted quadrates, where these Fi's are constants or I mean are first degree polynomials. So the algebra K is a subalgebra of the affine group. And at the end, what you get are algebras of vector fields and differential forms and of coordinates, which are can be described easily in terms of commutator and relation, in terms of generators and relations, and have the same Hilbert Poincaré series as the classical one. So we have applied the machinery to all quadrates of R3 in particular in a lot of details. And here I have just prepared some results for elliptic cylinders in Euclidean R3 or hyperboloids in cone in Minkowski R3. And in particular, when there is some additional symmetry, circular symmetry, you can also introduce a metric which is compatible with the Euclidean or the Minkowski deformations, which is compatible with the Euclidean and Minkowski metric. So in particular, if you do with hyperboloids, you get with one-sheeted hyperboloid cone and two-sheeted hyperboloids. The one-sheeted hyperboloid can be interpreted as twisted RDS2 under the Sitter space, and for C bigger than 0, larger than positive, and for C negative, the MC are union of two copies of twisted anti-de Sitter spaces, and well, the curvatures and so on remain essentially untwisted. So, summarizing, we have built via Drinfeld twists belonging to this special, this special Lisa algebra XIT consisting of vector fields annihilating the FA. We have built a general non-commutative deformation procedure of all submanifolds MC embedded in Rn. The twisted Cartan calculus on such submanifolds is equivalent at the the whole algebra of twisted diffeomorphisms. If we add a metric, twisting keeps all normal and tangent decomposition and essentially undeformed, and allows a projection of the Levi-Civita connection to the submanifolds, provided we take F. Sorry, I forgot to add here is U. Sorry, universal enveloping algebra. Yes, here I forgot to. Sorry, to put a U here. Sorry. U here and U here. Twisted algebraic submanifolds can be characterized in terms of generators and polynomial relations. Natural developments would be to study other quadrics in higher dimensional, or take a codimension larger than 1. Use other kinds of F, including real twists. I forgot to say that we have imposed everywhere where that a star structure exists using unitary twists, and we consider explicitly abelian unitary twists and Jordanian unitary twists, but one can do this also for real twists in the sense of Vasquez and al. Use Cn instead of Rn as ambient spaces. Use take submanifolds of projective spaces, deform them, or use more general twists in the setting of quasi-triangle, Hopf or quasi-Hopf algebras or bialgebroids, and then find physical applications, for instance, to non-commutative RDS spaces in cosmology or event horizons and so on. So let me conclude this talk with a final thought and a memory of John Mador, who I would say best summarizes the atmosphere and spirit of, together with George, the atmosphere and spirit of the summer institute, or Corfu Summer Institute. Here we have some pictures taken in the occasion of his 39th birthday, and he will always remain 39 in our minds. Thank you.
Thank you very much, Gaetano. Thank you very much. Questions, comments, remarks, please.
This is my yes.
Paolo, please.
We're here this week. Joachim Arnlind gave a talk on surfaces embedded in Rn, and he also is developing the differential geometry and the Riemannian geometry.
I didn't know because I arrived later.
So I think it would be interesting to compare the two approaches, because basic theme that of an embedding is present in both structures.
Okay, thank you. Yes.
Okay, any more questions? I do have one, if I may. So first is, well, the usual thing about the star structure. I mean, usually if you twist Rn, I mean, you for the product you have also the star structure. Does the star structure, I mean, you know, carries to the submanifolds, or?
Yes,
yeah.
We have to repeat always this thing.
Yeah.
And we are able to do this both with the unitary twists and with the real twists in the sense
Okay.
of power.
Okay.
So that this little piece for unitary twist was missing in the papers, so we added this little part. And I mean, the Jordanian twist of Oleg Ogilevsky, which we have used, is naturally unitary. Yeah. There is a natural counterpart, which is real, which is the one by Jacquin and Zhang, and one of the possible things one could do and that's real in the sense of one positive thing to do would be to adopt that one to 3. So if you relax the star structure, everything we have done can be applied to CN, submanifold CN, and everything is easier. So essentially, CN is done. The case of CN is done.
Okay, and a second short question, I mean, is, do you have, I mean, are the known examples of some, say, non-commutative manifolds like the, I mean, you can have the spheres like the quantum spheres with the with the complex of modulus 1 which are known examples of non-commutative manifolds realized as this submanifold.
You mean the one like the one of Voronov, which I showed at the beginning, when the ones where the bimodule of one forms is of one more dimension.
No. I mean about the manifolds. So, for instance, you can have this 3-sphere, say, made with deformed with parameter which is of modulus 1. So, can you realize that it's as a submanifold in your sense?
Of modulus 1, you mean you take
so something like SUQ2. So as SUQ2, but with Q being the complex number of modulus 1. I mean, this is
no. Wait, this does not apply still to quasi-triangular. I mean,
okay.
Yeah. So, for instance, the dr square or d of the determinant remains 0.
Okay.
So, to find this exotic phenomenon, one should extend, generalize the formalism to the quasi-triangular case. Okay. So we are not able to obtain exotic phenomena. Right. But I think this is, I mean, starting point as a reference before doing more complicated things.
Okay, thank you very much. I don't see any more questions, and I don't see any questions online. So let us thank Gaetano once again. And we have the transition to another local speaker. And we are very happy to have here Branislav Jurco from Prague, who will be talking about homological perturbation and homotopy transfer. Please, the floor and the screen are yours. Not the microphone, yes. So the transition of the speaker was smooth, but the transition of the microphone was not. Okay, now you're ready.
So thank you for the kind invitation and for the opportunity to give the talk here, which is based on some collaboration with late Martin Dobek, Lada Pexova, and Jan Fullman. Yeah, so since I used it in the title, the term homological perturbation, so let me tell you what is it about in the case you were not familiar. So what is the starting point? The starting point is what we call standard situation, abbreviated as SS, which is a pair of differential graded vector spaces with respective differentials Q and E. And what you need is a pair of maps P and I going like that way, and the contracting homotopy denoted as K, which acts on V. And these have these properties. Of course, Q's are differentials, so they square to 0, and in my conventions they are of degree 1. These are the chain maps P and I, so they interply between the respective differentials, and they are of degree 0. And the contracting homotopy is degree 0 or -1, such that it is really contracting homotopy between the identity on the V and the composition of P and I. So that's the property. If in addition to these conditions of the standard situation, these SS conditions, we have also one more condition, that the composition of I and P is identity on W, then we talk about deformation retract. And in addition to a deformation retract conditions, we have these three more conditions, that these compositions of P and K and I vanish, and K itself squares to 0, then we talk about the special deformation retract. And what is the perturbation lemma about? So consider a standard situation as before, and perturb by something small the differential Q here on the V, on the differential graded vector space V, so that we can get again something which squares to 0. And small doesn't really here mean anything because it's perturbation, so it's formal power series. So, you know, I'm always interested until some power in series. So what you can do? Well, the perturbation lemma does for you actually. It gives you a new map P prime, new map I prime, a new differential on the W, the transferred one, which is denoted as E prime, and a new contracting homotopy. And these are the formulas made with help of the geometric series, which is built up from the contracting homotopy K and the perturbation. So this is what people did in homological algebra, like, I don't know, maybe 60s or 70s. And so what is the claim? So the claim is that if you start with the standard situation, using this formula given by perturbation lemma, you get again a standard situation. If these maps, chain maps, P and I, are quasi-isomorphisms, or P is surjective or I is injective, these properties are preserved under the homotopy, I mean the transfer, the homological perturbation lemma. If in addition your starting data fulfill this condition, then starting from a deformation retract, you get a deformation retract, and it's like if and if. And finally, if you start with the special deformation retract, then the perturbation lemma gives you special deformation retract. So, okay. Since what we are doing is we will apply this to like Batalin-Wilkowiski formalism, we will assume that we have a symplectic form, degree -1, an odd symplectic form, in addition to our differential on the vector space. So if you think about, let's say, string field theory, Q would be the first the BRST operator, and omega would be like BPZ pairing, maybe with some insertions. And in this case, in the presence of the symplectic form, you can construct easily a special deformation retract. Simply consider the composition of your original vector space. This would be the first quantized string, Hilbert space, for example. In the piece which is the cohomology of the BRST, of the Q, of the differential, then into the image and into the complement. And you can make the choices in such way that this decomposition is compatible with the symplectic form. So the point is that your symplectic form restricts to the cohomology, so you get the symplectic form omega prime on the cohomology. You get another piece, which is the symplectic form on this direct sum of image C and the complement, such that both the image of Q and this complement are Lagrangian submanifolds here. The contracting homotopy, it's a partial inverse of the Q on its image. And obviously the maps, the chain maps P and I are the projections to the cohomology and inclusion on the cohomology according to the decomposition. So this is the so-called harmonious Hodge decomposition. So starting with this data, you have automatically a special deformation retract. And you can extend it actually to functions. So that makes it explicit on a vector space, so to the fields. So, I mean, there is a technical assumption that the grading of the differential of the DG vector space V is such that you know, the degree-wise components are finite dimensional, so that which is never true, of course, in quantum field theory in BV. But yeah, otherwise, the Batalin-Wilkowiski delta is not well defined, and you have regularized, maybe renormalized, so which is something to consider in the future. But still, Batalin-Wilkowiski delta is well defined in the string field theory. This is what Zwiebach told us. So if I take my symplectic form, and this is the inverse matrix, so I remember I had this part on the cohomology, a restriction to the cohomology and to this complement. Both are symplectic, so I can inverse, and I have two. Sorry, there are two primes. I have two Batalin-Wilkowiski deltas. These alphas, these are, let's say, homogeneous coordinates on the cohomology, and betas and gammas are homogeneous coordinates on the complement. So let's see, gammas would be like non-physical fields or states coordinates, and these will be the trivial ones. This is actually the image of Q, so the trivial and plus C, non-physical. And similarly, you have the Poisson bracket decomposes in two pieces which don't interact. One is on the cohomology, the primed, and one is on this complement. And yeah, to be, I mean, precise, I would have to speak not just on functions on V, but on some formal power series in some, let's say, H bar, formal variable, and actually some proper subspace. But yeah, I just will not bother about this, but you can make it kind of precise. Well, okay, so there is this lemma that you can extend actually. So you remember, you started with the differential graded vector space, the differential and the symplectic form, and you had automatically a special deformation retract, and there is a way which is called the Penzo trick. It goes back to Eilenberg and MacLean, how you extend it to the functions. And in these coordinates, I introduced these alphas on the cohomology, betas and gammas on the physical and trivial subspaces. Here are the formulas. So you extend them as first order differential operators. This is the extension of Q, and it is given by the Batalin-Wilkowiski bracket with the function, with the Hamiltonian for that, and this will be become the free part of the action. So this is the contracting homotopy. Well, so there is either X too much or X missing here. So this is formed as, you know, with the partial inverse of the Q, but it is not really a differential. Like a derivation, sorry, it's not a derivation because it is normalized. Well, this is, you need it for to be partial inverse to get one. So you have divide by the numbers of and betas of gammas after you applied it to a function of alphas, betas, and gammas. And yeah, you construct these chain maps using the original projection and injection on yeah, between the vector space and the homology. And maybe for the later reference, I also use the notation k with index 0 will be unnormalized. That will be really derivation. Now, what I will describe is homotopy transfer for quantum version of L infinity and A infinity and whatever kind of quantum versions of homotopy algebras or even super algebras, which come as a Feynman transform of some modular algebras over the Feynman transform of some modular operands. For some purposes, they need to have some extra structures, which is connected sum. But yeah, I will ignore this detail for the rest of the talk. And even if you don't know what these quantum homotopy algebras are, you shouldn't worry, because yeah, in actually series of papers starting with Zwiebach and continuing with Markle, and then in the general case papers by Baranikov, there is established kind of one-to-one correspondence between this homotopy, quantum homotopy algebras, which comes from these modular operands and their Feynman transform, and solutions to quantum master equation. So how it goes? So obviously this, you have seen L infinity algebras, or maybe even Q L infinity algebras. There were talks using these objects. So you have operations. So these are n-array operations, which take like n vectors in your underlying vector space and produce again a vector. But now in the quantum case, you have these n-array operations. They are labeled by another label, which kind of correspond to the genus. So this is why the quantum comes here. And how these are related to the solutions to the quantum master equations. So if you take these operations, apply them to fields which I denote collectively like phi's, and you use symplectic form, then you get a function. Yeah, and the solution to the quantum master equation translates to algebraic relations on these n-array operations. Okay, so what I would like to do, use the homological perturbation lemma to perturb the free differential to the BRST differential and see what it is. So what I can do, I can either start with the free BRST operator, and I can perturb it with Batalin-Volkovisky delta, and just apply the formulas of the homological perturbation lemma. So in this case, I have a new map P, a new projection, which is built up from the original one and from this geometric series, and I can apply this to the exponential of the interaction part of my action. And what I get is an effective action. So this will be function on the cohomology, that is this projection, which will satisfy the quantum master equation on the cohomology. So essentially it tells you that you have an S matrix on the physical states, and these are the word identities. And you can bring it to the standard thing you know from the quantum field theory. because under this projection, well, this is several ways how you can show it, either doing combinatorics or on some general nonsense kind of arguments. You can show that it is the same as you would exponentiate the propagator and apply it to the exponential of the interaction part. So essentially what the homological perturbation lemma does for you, it computes for you Bataillon-Wilkowski path integral. And similarly, you can apply it to the product of a function and the exponential of the interaction part, and you get an effective function. So it does the unnormalized path integral. Now you can perturb with the second type of perturbation, so you add even the Hamiltonian vector field corresponding to the interaction part. And then you get the new projection. Again, just take the formulas and you get a new perturbation and a new projection. And the new projection now is related to the one when you perturbed only with Bataillon-Wilkowski delta in this way. And you see that homological perturbation lemma gives you directly normalized path integral. Now, how it relates to homotopies, since part of the title was homotopy transfer. So what you do is you tensor your functions with just forms on the interval, on the unit interval. And so you say that combination of AT and BT, where BT is now degree -1, is a homotopy between A evaluated at 1 and at 0 and 1. If your AT solves quantum master equation for all t's, and if the time dependence is given by this equation. And so what you can easily see, it's more or less standard thing, is that if you have two functions, S1 and S2, like two actions or two interacting parts, the following statements are equivalent. There is a homotopy in the sense above between them. There exists such a function that the difference of the exponentials is like exact with respect to this Bataillon-Wilkowski operator perturbed with the Hamiltonian vector field. Or there is a symplectic diffeomorphism starting with the identity, which relates these system identities with two different interactions parts. And so there is this kind of interesting maybe comment that even the simplest homotopy works. And of course, the phi is generated by the Hamiltonian vector field generated by this B. Yeah, given here. So now we can interpret the construction of the effective action as a homotopy. So you just recall the first version of the perturbation lemma when I perturbed with Bataillon-Wilkowski delta. So you have a new contracting homotopy, the new differential, the new projection, and the new injection. And you just apply this formula straightforwardly to the exponential of the interaction part. And what you see that it gives you a homotopy between the effective action and the original action. And in this case, actually, what you have is a change of coordinates which intertwines between the half densities, where you know that phi is exactly generated by this homotopy AT and the new contracting homotopy given by the perturbation lemma. And actually, it tells you that you have a decomposition theorem for quantum L-infinity algebra. So you have an isomorphism between two quantum L-infinity algebras, one defined, by this original one and one with the effective action, such that here, in the sense, you get a minimal model because it gives you quasi-isomorphism, and well, all the differential is just acting on the free action, and there are no operations on this part. That's the free piece. So it proves for you also the decomposition theorem for quantum L-infinity algebra. Okay, there is a lot of other things now which you can do starting from that observation, which I hopefully can tell you at some other occasion. Okay, thank you very much.
Okay, thank you very much. And questions? Please.
You had these two deformations. You had these two deformations.
Yes, yes.
Is it possible to just indicate the order? First in.
Yeah, you can. Yes, yes. In principle, yes, yes, yes. You can do, of course. Yeah, yeah.
Okay.
Any more?
Yeah, you get like the, you know, if you forget about the delta, you just at the interaction you get an L infinity morphism, would be classical. Yeah, 3 level.
Okay. Any more questions from the audience here in Corfu? No, I don't see. No, I don't see any questions. I think there are no questions online. Am I correct? No questions online. So thank you once again.
Yeah, thank you for your attention.
And we'll move to the next speaker and the last speaker of this before lunch session in our workshop. And this is Tomasz Brzezinski from Swansea, who will talk. We need to stop sharing, and Tomek, you need to.
Yes, exactly. So I can start sharing when you stop sharing. So I will start sharing now.
I think, yeah, now you can start.
Mm-hmm.
Oh, yes. Okay, so welcome again. We just still don't see it.
Sorry, you can't see it.
No, we see
again.
the screen.
Okay, usual problems. Stop sharing, and I will start again. Let's try to do it that way.
Still black screen.
I know, but something white should appear soon.
Yes, yes. Now we see it. So welcome again, Tomasz Brzezinski with Heaps of Connections. Please, the screen is yours, and I give you the warning after 20 minutes.
Thank you, Andrzej. Thank you, George, for inviting me to give this talk. I'm sorry I can't thank you in person, but you know, my university here cares so much about us that still we are not allowed to travel to conferences. Anyway, maybe some other time. Right. So before I start talking, I just wanted to say, as a workshop devoted to the memory of John Mador, I haven't met John that many times, but I very much admire his book, because I think that John had this wonderful ability of explaining in a very simple terms very difficult mathematical concepts. And I believe that as mathematicians or mathematical physicists, we should always strive to explain whatever we are doing in the most accessible terms. So I'm pretty sure now that the pity that I have to say it in the past tense that John had this ability, but I'm sure that somewhere in heaven, angels are now playing with non-commutative geometry and fuzzy things. Now, going back to the topic of my talk, well, you can see it's heaps of connections. So what is the problem here? So everybody knows what an associative algebra is on a vector space. Okay, so it's a vector space, say A, right, which has a bilinear associative multiplication. Now, as a consequence of the bilinearity, we have usual distributive laws. So the multiplication distributes over the addition of vectors in our vector space. Now, the question that I tried to answer for some time is how about replacing the vector space by an affine space in the definition and demand that the multiplication, which would be an associative operation, but will no longer be linear or bilinear because A is no longer a vector space, but we have affine transformations. So suppose that we have the affine property on both legs in the multiplication. So what kind of structure we get? What kind of algebra we will get in that way? Right, so one can ask, and probably rightly so, why bother at all about this? But if you think you're in the concepts of geometry, then to study connections, say a vector bundle, the connections do not form a vector space. You can't add the connections to get a connection, but they form an affine space. So how about trying to find an algebraic system that would allow us to multiply connections? Okay, so before I start describing what kind of system you get there, let me just remind you about affine spaces. So you can think about an affine space as a two-dimensional Euclidean space, a line, which not necessarily crosses the origin. Okay, so right, so with this line, it is a line, so there is an associated vector space. So in general, in an affine space, you have an associated vector space. So A is my affine space, V is an associated vector space, and to any pair of points in your affine space, you can uniquely associate a vector in V. And in fact, any vector in V can be seen as associated to 2 points. So normally we would say about the difference of 2 points on an affine space would give us a vector. And any point in an affine space, if for any point we take a vector from V, we can shift the point to another point. Okay, so in particular, if I have 3 points in my affine space, I can form a vector of 2 of them and add this vector to the first point. And as is every vector can be rescaled. You can add vectors, but we can also rescale vectors. We have a scale multiplication. So we can see this combined operation here that I have one point and take another point. I can rescale the difference between the new point and my original point and shift my original point by this rescaled vector. Okay, so this formulation, so what I wrote here, I wrote it on purpose in such a way that I'm not really avoiding binary operations, but I'm avoiding in this A to B vectors. I associate the structure entirely with to points in an affine space. I usually thought about affine space as a connection with a vector space, but you can formulate the definition of an affine space without reference to any vector space. So we can get rid of V together, but there is a price we should pay, or we will pay. And this price is not a large price, but we have to work with ternary operations rather than binary operations. We have to replace addition of vectors by a Turner operation. Okay, the idea goes back to almost 100 years to Prefer and Baer. So it's probably one of the last chances to write references to 1924, which is putting the apostrophe 24, because soon we have to clarify which century we have in mind. Right, but Prefer and Baer introduce the notion of heap or herd, or later on it's also known and in a more geometric context as a torsor. So what is a heap? A heap is a very simple algebraic system which consists of a set. I say here it's a non-empty set, but you don't need to assume being non-empty, which has a Turner operation defined on it. And this Turner operation satisfies just two conditions. One is the associative law, which tells you that if you apply if you take 5 elements in your set and apply the Turner operation to the first 3, so then reduce the 3 to just 1, you can apply the Turner operation to the result, that's the left-hand side. You will get exactly the same expression as if you first apply the Turner operation to the last 3 elements and then apply the Turner operation second time. So it's some sort of associative law. If you can shift this bracket by 2, not by 1, by 2. And the second axiom that are called Marcev identities, which tell you that if 2 points meet in the bracket, they will produce the third point. Okay, the heap is said to be abelian if we can swap the first with the third entries. Right, and homomorphism of heaps, as always in algebraic structures, it's a function which respects the operation. So f applied to the Turner operation gives Turner operation applied to the arguments. And you might think that heaps are something unusual and not very common, but in fact, any abelian group or any group is a heap, and any abelian group is an abelian heap. And the Turner operation is just the combination of addition and subtraction. Okay, combination of, well, you add to the first element the inverse of the second, and then add again the third element. Okay, so now I'm coming to the main definition of the talk, which is the heap of modules. Okay, so you remember in the so maybe I should go back to the example of the affine space. So if you look at the first axiom here, in the affine space we can't assign a point to a pair of points, but we have an operation which takes a triple of points and assigns a point in an affine space. And now the second operation that I will introduce mimics this shifting by the rescaled vector. Okay, so in general, we can start with a ring and a heap. So A is a heap, R is a ring. And the heap of morphism is this pair, or A, with the, again, operation acting on 3 arguments, where this lambda is a morphism of heaps on the first and the third arguments. You might ask why it is not a morphism of heaps on the middle argument, but actually it is, but it's a consequence of the other axioms. It is associative, so if you rescale, if you multiply in ring, then it's the same as applying this lambda twice. And it also satisfies this base change property, which essentially in the affine situation means that you can, if you have a pair of 2 points and you rescale the original point by the difference of the 2 points, then you can pick another point, rescale the vectors, and add, subtract, and get the original rescaled point. sorry, shifted point. And the morphism of heaps of modules is a morphism of heaps, which commutes with the actions. So lambda is just plays the role of the action. Okay, so going back to the affine situation. So an affine space is a heap of modules over a vector space F, or over a field F. The Turner operation is just given by a point shifted or translated by the difference of two other points. And this action is given just by shifting a point by a rescaled vector difference between this point and any other point. Now it turns out that also the morphism of heaps of modules, or the morphism of affine spaces, is a morphism of the heaps of modules. So just to remind you what a morphism of affine spaces is. So if we have in the traditional formulation, if we have these two affine spaces, one over the vector space V, the other on the vector space W, then a morphism of affine spaces is a function which induces a linear transformation between the corresponding vector spaces, which has the property that whenever you apply it to the difference of 2 points in the first space, you will get a difference of the applications of F to the points. Now the differences in the other affines or other vector space. And in fact, this requirement of the existence of F hat, the linear transformation, is equivalent to saying that F is a morphism of heaps of modules. Right, so the lesson from this part of the talk is that if you have a affine space, normally it's defined over a vector space, but you don't need to do it. You can define an affine space entirely in terms of the affine space itself, the set on which the affine structure is defined, the price you pay for this is to use Turner operations. Okay, so let's give. I will give you an example of the which goes beyond an affine space, and that's the heap of connections. So I'm already at the title of my talk. So suppose that we have two algebras, A and B. We have a differential graded algebra on O and B, and we have a differential graded algebra on O. So the differential structure on it, the differential calculus, and everybody knows what a connection is. So M is so I will assume it's an OB bimodule. And by gamma of M, I will denote the set of all connections, left connections. So these are maps from M to omega 1 of O to tensor M, which satisfy the usual connection Leibniz rule. And then what you can easily find out is that, of course, the sum of the connections will not be a connection. But if you take the combination of the sum and the difference, you will get a connection. And furthermore, there's an action of B, which is given in the way that I just underlined. And with these two operations, we have a heap of modules over B. Now, you might say that this B is somehow artificial, but you should remember that whenever you have a module, one-sided module, and it's an O module, say, on the left, then you can look at the algebra of endomorphism, linear endomorphism, or linear endomorphism of M, and this will act on the other side in the compatible way. So in every situation that you find yourself, there is if you have a one-sided module, actually there is a natural algebra acting on the other side, and every subalgebra of this will act as well. Right, so now going back to the question that I asked on the second slide, that is what kind of structure we get when we ask an affine space to have a associative multiplication, which is an affine transformation. Okay, so we have an affine space and this function m, the multiplication, which is associative, but I want this to be by affine transformation. So in the first place, it has to respect the heap structures. So respecting the heap structure on the left argument means that we have this sort of distributivity between multiplication and this ternary heap operation. On the right, we have the distributivity of on the other side. So we have some kind of distributive laws on this affine space with associative by affine multiplication, but this is not it's not a usual distributivity over the addition, because there is no addition in the affine space, but over this ternary operation. And a system like this, a set with associative multiplication, well, a heap, a abelian heap with associative multiplication, with this kind of distributive laws, is known as a truss. Okay, so everybody knows what a truss is, and you've seen many trusses in your life, I'm sure. And the trusses go back to ancient times. So there's an example of a truss appearing in an Egyptian ship. Well, they used trusses in cathedrals. They were used to support the roofs. A lot of bridges have trusses. Even you can find trusses in the nature. So apparently those flowers have a structure which is for some reason known as a truss, and also in the outer space. So there are plenty of trusses everywhere, and it's quite an ancient structure. Okay, so let me make a couple of comments on the definition. So in a ring, the associated distributive laws immediately apply that multiplication by 0 gives you 0. Okay, that's why we can't invert, we can't divide by 0, because multiplication by 0 will always give 0. Now in the truss distributive law, which would look like that if you start with an abelian group and take the ternary operation composed of difference and additions, this does not imply that A0 is equal A times 0 is equal to 0. Okay, so in a truss, you have a lot of more ability to consider more operations, compatible operations, than in a ring. So for example, if you take any abelian group, you can make it into a truss by declaring that multiplication is the same as addition. Now the interesting point in this example is that you can divide by all elements, because division here is the same as subtraction. You can define so kind of skew type multiplication, where A times B will always pick up the first element, A. Again, this is not a ring. This is never a ring, unless the ring has just one element. The same is true about the other one. And you can define multiplication by picking any constant element. Again, this only becomes a ring when this constant is chosen to be 0 in the abelian group. But so what the conclusion of this is that there are many more trusses than rings. And as an interesting example, a sort of odd example, is that if you take odd integers, then of course we cannot, if we add to odd integers, we will get an even number. So odd integers do not form a group with respect to addition. But if you subtract the third integer from the other two even one, you will get another odd integer. So the ternary operation is well defined, and the usual distributive laws of arithmetic imply the distributivity over the ternary operation. Okay, so one more example you know, when we start algebras, we have algebras of matrices. So let's have a look at the corresponding notion in the affine situation. So if we consider matrices of this form, this particular form, where you have a block matrix here, then there is a column A and one sitting at the in the right-hand bottom corner, then of course this is not an abelian group with respect to addition, because, for example, 0 matrix is not there. But if you take 3 such matrices and add them and subtract them, then you will get a matrix of the same shape. So you can you have the Stirner operation, and okay, and then this is an affine space where for the vectors, what you take as a vectors, associated vector space, the vector space of n plus 1 times n plus 1 matrices, where there is only the left-hand corner is non-zero. Oh, sorry, I should say here, this 1 is not here, but is 0 in the vector space. So if you take the difference of 2 matrices of this shape, you will get a matrix in which the bottom row consists of zeros entirely, and this is obviously a vector space. And this you can easily check that this space of matrices of the form like that is closed under multiplication. So indeed, you have a truss, and it's an affine space on which you have a bi-affine, defined by affine multiplication. Okay, so one can ask what trusses are good for, apart from giving us a chance to cross the rivers and to admire nature and architectural marvels. So in mathematics, the trusses appear in, and that was the main motivation why the notion was introduced in the recent studies of the solutions of the Young-Baxter equation. And well, to be precise, the set theoretic version of this important equation. And it was noticed first by Rump and then by Sedo, Jaspers, and Okniński that there is a one-to-one correspondence between the solutions of particular type and algebraic systems called braces. So on the set on which you find the solution, you have 2 group operations which commute distribute one of the other in a particular way, which is in the way that is described by a truss.
Let me interrupt you just to let you know that you're close to your time.
Okay, so and I'm close to the end of my talk. So the other applications, if you want to study ring extensions, then rather than studying the ring extensions, the sequences of rings, you can associate trusses. And another application which I will mention on the next slide is the cross products of ring by one-sided modules. So normally when we want to extend rings, we use a two-sided module. But in this, if you enter the world of trusses, you don't need to have two-sided modules. Right. So the basic observation here is that if we have a heap of R modules, we start with the ring or an algebra, associative algebra, and we have this heap of modules. Then we can construct on the cross product A with R, the Cartesian product, a truss in the following way. So the Turner operation uses the Turner operation of A in the first leg and the usual addition subtraction in the second leg. So the second leg is in the ring, and the multiplication, well, uses the action of the ring on on the heap of modules on the first leg and the usual multiplication. Okay, so if I apply it to the situation of interest in non-commutative geometry, say, so we have, so going back to the example of connections, we have two algebras, differential calculus over O, and a set of connections, which we know it's a heap of modules over B. So gamma of M is a heap of modules over B. Those are left connections over O. And we know from Kunz and Quillen that if the module is finitely generated, then the connections exist. And one way of constructing such connections is to take the dual basis for our projective module, or the projector, if you like, the idempotent which gives you the module, and that's how you construct the connection. Okay, so whenever you have a situation like this, whenever you have a finitely generated projective module, you can associate to the set of connections a multiplication, which will distribute, which will be an associative multiplication, which will distribute over the ternary operation of adding and subtracting of connections. So that's the way of multiplying connections and putting them in a consistent algebraic structure. So one final slide of contents, just to summarize what I have said. So normally we define affine spaces as related to some vector space, but we can get rid of the vector space, define everything in terms of the affine space alone. Then we can derive out of it a vector space by using ternary operations rather than binary operations. And these ternary operations they form lead to a heap, and then the heap of modules, and an affine space which has a bi-affine multiplication becomes a truss. So we have a sort of distributivity, but over the ternary operation. And if you have a heap of modules over a ring R, you can combine it with the rings to make a truss out of it. And then, in particular case, you can do it for connections in classical or non-commutative geometry. So, just to finish, the references. Thank you very much.
Thank you very much. Now, questions, comments, remarks, please. Paolo?
Hi, Thomas. This is Paolo. Thank you for
Hi,
your...
Paolo.
And so I have a very a crazy question. So let me ask it to you. What you have told us, to me, seems a way to avoid speaking of a group action. In this case, a vector space acting on a affine space. And I was wondering whether you are thinking of, or there are some, one could think in going in the direction of also revisiting, for example, the notion of principal bundle in such a way that you don't have a group acting on such a principle. Mm-hmm. And so, yes, this is my question.
Yeah, I mean, you know, heaps appear in precisely in this context in geometry where they are torsors. So they are the way of formulating principal bundles without mentioning the group.
Yes, it's mentioned.
Covered. So the idea is that you put going back to the definition of a heap. So that's a way of putting several isomorphic groups together. If you pick any point, so going back, maybe I should show the slide with the definition. Okay, so I mentioned here that if you have a heap, if you have an abelian group, then you will have a heap.
Yes.
But the other way around is also true. If you have a heap, say non-abelian, general heap, and you fix the middle entry, okay, so say here, you fix the middle entry, then you will get a binary operation. Okay, B stays fixed, and you think about the operation on A and C. And fixing the middle term, you get a group where this middle term becomes the neutral element for the group.
Yes.
And so if you think, in terms of bundles, that's exactly what happens if you don't want to, you can get to the fiber at where fiber is a group. So you can, by picking the point on your underlying manifold, the base manifold, you can get to a group which sits over this point, and that's exactly what happens in this algebraic setup. So you can, so the answer to your not such a crazy question is yes, this can. The origin really comes also from geometry of principal bundles.
Thank you.
Okay, thank you very much. Any more questions? I don't see any questions. I don't see any questions online. Let us check once again. No, there are no questions online. So let us thank one again for this nice talk.
Thank you very much. Enjoy your lunch.
Last talk of the morning before lunch session. So let's thank once again to all the speakers in this session. So thank you very much. And for those of you who were remote, see you next time in person in Corfu.